Welcome to today's paper reading. Today's paper is titled DocLLM, a layout-aware generative language model for multimodal document understanding. This paper was published on the AR14 preprint by Dongsheng Wang and colleagues from J.P. Morgan AI Research. This paper introduces DocLLM, a lightweight extension to traditional large language models designed for reasoning over visual documents. Unlike existing multimodal LLMs, DocLLM avoids expensive image encoders and instead focuses on bounding box information to incorporate spatial layout. The model decomposes the attention mechanism in transformers to better capture the cross-alignment between text and spatial modalities. Additionally, a pre-training objective is devised to infill text segments, addressing irregular layouts and heterogeneous content. The pre-trained model is fine-tuned on a large-scale instruction dataset covering 4 core document intelligence tasks. Results show that DocLLM outperforms state-of-the-art LLMs on 14 out of 16 datasets, and generalizes well to 4 out of 5 previously unseen datasets. The paper introduces DocLLM, a novel approach to document intelligence. It addresses significant challenges in document AI, such as the performance gap in real-world applications, focusing on accuracy, reliability, contextual understanding, and generalization to new domains. Unlike traditional large language models, DocLLM is a lightweight extension that excels in visually rich form understanding tasks. It models both spatial layouts and text semantics, reducing processing times without relying on complex vision encoders. The paper also presents innovative solutions, including a disentangled spatial attention mechanism, an infilling pre-training objective tailored for irregular layouts, and an instruction tuning dataset specifically curated for visual document intelligence tasks. Figure 1 illustrates the key components of DocLLM. Firstly, the input documents consist of text tokens along with their bounding boxes. Secondly, the attention mechanism of LLMs is enhanced to capture dependencies between textual semantics and spatial layouts. Thirdly, infilling text blocks is employed as a pre-training objective to handle irregular layouts. Lastly, task adaptation is conducted using a newly curated dataset of instructions. The remarkable success of ChatGPT has spurred significant research interest in large language models, LLMs. Text-based LLMs, such as BERT, GPT, and T5, were foundational, with ChatGPT and GPT-4 representing significant advancements in model size and data. Multimodal LLMs, which integrate visual input, include general-purpose models and those tailored for visually rich document understanding, VRDU. Recent models like MPLUG-DocOwl and UReader show strong zero-shot generalization. Our proposed model, DocLLM, addresses the limitations of unimodal and complex multimodal models by explicitly modeling spatial layouts and text semantics, resulting in a more efficient and compact design. Figure 2 illustrates the architecture of the DocLLM model, which integrates a disentangled spatial attention mechanism and an infilling objective. On the left, the input document is shown with text tokens and their corresponding bounding boxes. Some text segments are randomly masked, and the model predicts the tokens in these masked segments autoregressively. On the right, the infilling sequence is depicted, where sampled segments are replaced with M and prepended with S. The attention mechanism is extended to account for cross-attention between text and spatial modalities, enhancing the model's ability to understand visual documents. The DocLLM framework is built upon an autoregressive transformer language model with a causal decoder structure. It incorporates multi-head self-attention layers and fully connected feed-forward networks. Unlike standard language models, DocLLM is multimodal, integrating visual information through OCR-derived spatial positions and dimensions of text tokens. This spatial information is treated as a distinct modality, represented by separate vectors, and the self-attention mechanism is extended to compute interdependencies in a disentangled manner. During pre-training, DocLLM employs a text infilling objective that leverages contextual information better than traditional next token prediction. Instruction tuning is performed on various DocAI tasks using diverse templates to enhance zero-shot generalization capabilities. Table 1 presents the prompt templates utilized for instruction tuning, excluding spatial tokens. The templates are designed for various tasks such as visual question answering, VQA, natural language inference multiple choice question, LLMCQ, and key information extraction, KIE. Each template is structured to guide the model in processing document-related queries effectively. For instance, the VQA template is formatted as document question, while the LLMCQ template asks a statement question with a yes or no response. The KIE extraction template queries for specific values associated with given keys within the document. Table 2 provides an overview of the statistics for the pre-training datasets used in the study. It includes details on the number of documents, pages, and total tokens for two primary sources, CDIP and DocBank. CDIP consists of over 5 million documents and more than 16 million pages, while DocBank includes 500K documents, each with a single page. The total number of documents across both datasets is approximately 5.6 million, with a combined total of 16.8 million pages and 3.9 billion tokens. Table 3 provides a detailed breakdown of the datasets used for instruction tuning across various tasks in Document AI. The tasks include visual question answering, VQA, natural language inference, NLI, key information extraction, KIE, and classification, CLS. The table highlights the number of training and testing instances for each task, showing a total of 635,883 training instances and 96,919 testing instances across all tasks. This data is crucial for understanding the scale and distribution of the datasets used to fine-tune models for specific document-related tasks. The experiments in this study utilized data from two primary sources: the CDIP Test Collection 1.0, which includes over 5 million documents and 16 million pages, and DocBank, which consists of 500,000 documents with each document featuring a single page. This results in a total of 16.7 million pages and 3.8 billion tokens used for pre-training. The models evaluated are two variants of DocLLM, DocLLM 1B, based on the Falcon 1B architecture with 24 layers, and DocLLM 7B, based on the Llama 2-7B architecture with 36 layers. Both models undergo pre-training and instruction tuning. The evaluation is conducted under two settings: same datasets, different splits, SDDS, and same tasks, different datasets, SDDD. Baselines for comparison include zero-shot, ZS, and state-of-the-art, SOTA, large language models, LLMs. Table 4 details the model configuration and training hyperparameters for two variants of DocLLM, DocLLM 1B and DocLLM 7B. DocLLM 1B, based on the Falcon 1B architecture, consists of 24 layers, 16 attention heads, and a hidden size of 1,536. In contrast, DocLLM 7B, based on the Llama 2-7B architecture, has 36 layers, 32 heads, and a hidden size of 4,096. Both models utilize float 16 precision and a maximum context length of 1,024. The table also outlines the specific learning rates, warm-up steps, scheduler types, weight decay, and atom optimizer parameters used during pre-training and instruction tuning phases for each model. Table 5 presents a performance comparison in the SDDS setting against various multimodal and non-multimodal LLMs. Non-multimodal LLMs are evaluated using zero-shot, ZS, prompts, while multimodal LLMs are instruction-tuned on the trained split of the datasets. The table highlights that DocLLM 7B excels in 12 out of 16 datasets, outperforming equivalent models in 14 out of 16 datasets. Specifically, DocLLM demonstrates superior performance in layout-intensive tasks such as KIE and CLS. In VQA and NLI, its performance surpasses that of most multimodal language models, although it underperforms compared to GPT-4. DocLLM 1B demonstrates performance close to that of the larger model, suggesting that the smaller model can derive significant benefits from the architecture of DocLLM. In this ablation study, we evaluated the three main contributions of DocLLM. First, we examined the effect of disentangled spatial attention by setting the lambda hyperparameter to 0 or 1. Results showed that maintaining only spatial-to-spatial interactions, lambda s equals 1, yielded the highest next token prediction, NTP, accuracy. The text-only self-attention mechanism performed the worst, emphasizing the importance of spatial features. Second, we assessed the autoregressive block infilling objective against conventional causal learning. Block infilling with spatial modality demonstrated the best performance, with spatial modality significantly enhancing causal learning. Lastly, we compared the prefix decoder with the causal decoder. While the causal decoder showed a slight advantage, the differences were marginal, suggesting that both masking methods are effective for document modeling. Table 6 presents a performance comparison of various models on 3 held-out VRDU datasets under the SDDD setting, contrasting them with non-multimodal LLMs. The table includes metrics such as DocVQA, KLC, KIE, VQA, and CLS, and covers model sizes ranging from 1B to 1T. This comparison highlights the effectiveness of different models in handling multimodal tasks within the specified datasets. Table 7 presents the results of an ablation study on disentangled spatial attention, focusing on cross-modal interactions. The study reveals that the configuration with only spatial-to-spatial interaction, S2S, yields the highest NTP accuracy, at 39.12. In contrast, the text-only self-attention mechanism, T2T, results in the lowest NTP accuracy, at 35.43. The performance differences among other configurations, such as text-to-spatial, T2S, and spatial-to-text, S2T, are relatively subtle, highlighting the significance of incorporating spatial features for document understanding. Figure 3 provides a simplified illustration of the attention masks used in the causal decoder and prefix decoder models for the purpose of block infilling. The figure highlights the differences in how attention is managed in these two types of decoders, which is crucial for understanding their respective roles in the block infilling process. The causal decoder uses a mask that ensures each token can only attend to previous tokens, while the prefix decoder allows for a more flexible attention mechanism, enabling tokens to attend to both previous and subsequent tokens within a defined prefix. This distinction is key to the effectiveness of block infilling in these models. Table 8 presents the results of an ablation study focused on the block infilling objective. The study compares 3 configurations: causal learning with spatial modality, and block infilling with spatial modality. The data indicates that block infilling with spatial modality achieves the highest NTP accuracy at 39.1, followed by causal learning with spatial modality at 36.2, and causal learning at 32.6. This suggests that incorporating spatial modality significantly enhances performance, particularly when combined with block infilling. Figure 4 presents a performance comparison on the next token prediction, NTP, task between the causal decoder and the prefix decoder. The results indicate that the causal decoder has a slight advantage over the prefix decoder across various configurations. This minor difference suggests that the bidirectional attention enabled by the prefix decoder is not critical in this context. Consequently, the causal decoder is preferred for all experiments in Section 4. The authors propose that DocLLM has the potential to significantly impact generative pre-training by allowing language models to process more than just plain text. This is achieved by accommodating complex layout structures, which enables the inclusion of documents like e-books and e-publications into the pre-training corpus without extensive pre-processing. The model's ability to understand documents of various lengths is enhanced by its multi-page awareness, addressing limitations of previous models. Future work includes practical comparisons of OCR engines and further refinement of zero-shot methodologies. Additionally, the authors share insights on training optimizations, noting that higher weight decay and a cosine scheduler tend to improve performance. In this paper, the authors introduced DocLLM, a lightweight extension to traditional large language models designed for generative reasoning over documents with rich layouts. Unlike existing multimodal LLMs, DocLLM strategically omits costly image encoders, instead prioritizing bounding box information to effectively capture the spatial layout structure of documents. This is achieved through a disentangled attention approach, which decomposes the attention mechanism in classical transformers and enhances it with cross-alignment between text and spatial modalities in structured documents. The model addresses challenges posed by irregular layouts and heterogeneous content by employing a pre-training objective that focuses on learning to infill block texts. The authors fine-tuned the pre-trained model using a comprehensive instruction dataset. Evaluation across various document intelligence tasks demonstrates that DocLLM surpasses equivalent models on known tasks for 14 out of 16 datasets and exhibits robust generalization to previously unseen datasets in 4 out of 5 settings, affirming its efficacy in extracting meaningful information from a wide range of visual documents. In future work, the authors plan to infuse vision into DocLLM in a lightweight manner. Thank you for watching.